Hello everyone, welcome to the lecture 4 of Comsol Multiphysics training course. In this lecture, we study the bending of a hyperelastic beam under local buckling. Before we start, we need to have some definition as usual. In this study, we will consider parameter sweep as a very important tool in Comsol Multiphysics to vary a parameter while we have a simulation. The parameter sweep does not catch the speed of variation, so basically we cannot see the effect of the speed of varying a parameter. We only see when we change something how it will change our results, and we can have very interesting results out of parameter sweep, such as videos which we will study in this example. So before we start, I want to introduce some concepts of hyperelastic materials. Hyperelastic materials are the materials that do not follow linear elasticity models. Some of the examples are tissue, rubber, many other elastomers, and anything similar to them. In order to model hyperelastic materials, we need to use other models. Some of the famous models are Neo-Hookean, Mooney-Rivlin, and so on. The libraries of Comsol will provide us with a variety of models so that we can use them to model a hyperelastic material. In order to study the bending or buckling of the structure, I would expect that you may know the concepts of bending or buckling in beams and columns. The concepts like critical load, global buckling, and local buckling are something important that you may find on internet. In this study, we want to model the bending of a rubber, which is a hyperelastic material. As we apply force from the two sides, we make a sort of bending on it, and as you see, because it's a rubber and it's a hyperelastic material, we have a huge bending on the structure. So in order to model this, we have to simplify our problem. Before I show you how to simplify it, I should say that in many mechanical or even other problems in Comsol, we have to identify the problem and the physics properly before we go into the software and model it. For example, for this problem, we can use the concepts of local buckling. In this example, we model the rubber as a beam which is clamped from one side and a force is applied from the other side. As you see, I applied a hinged boundary condition to restrict the motion only in x-axis. And as you see, the force is applied to one corner. As you see, it's not fully in the center, because the application of the force on the center and a full symmetry on applying the force may cause a global buckling rather than a local buckling. Like I said, you may find more information about local buckling and global buckling on internet. So as I said, in this study, we have to model the system based on the local buckling of columns. And in order to model the material, if you do some research on rubber, we can use a Mooney-Rivlin 2-parameter model. And for the rubber, we have the C110 and C01 as defined here. And finally, we need some other information about the material, such as bulk modulus and density. So these are the parameters that we are going to use in the simulation. So let's get into the software and do the simulation. Okay, same as before, we click on Model Wizard, and then we are going to use a 2D model now and continue. I am gonna select solid mechanics and add and wait until it is added to our physics interfaces, and then continue with the selection of study. There you go, it's here. We click on study, and then we are going to use a stationary model. Like I said in the slides, the parameter sweep is not going to catch the speed of variation. It only models when we change a parameter and see the effect of changing the parameter on the results. So we can use it on different studies. For now, I'm going to select the stationary and done. Let's get into the software and do the modeling over there. Okay, now before we select the geometry and make our model, I want to introduce you with a parameter definition under global definition. If we click on parameter, we have a menu here to define our parameters. It is a very important and interesting feature of Comsol where we can define parameters and then we can use it in our components. Not only if we have only one component, we can use them in different components. For example, in here, I want to define the geometry parameters and the parameter that we are going to sweep on in this section. So I'm going to define W1 as the width, which was 15 millimeter in the slides. then we have h1 as the height of the rectangle, which was 0.5 millimeter. And as you can see, we have a very slender rubber beam which requires a tiny force to be bent. And we have d1 as the out of plane thickness as 10 millimeter. And I should also define the parameter that I'm going to sweep, which is the force. I just use F, and in here I'm going to use 0 Newton. So 0 Newton is defined as the force, but don't worry, we are going to change it in a range of forces. So for now, let's use 0. That's it. Now we can continue with the geometry. I'm going to right click and select a rectangle, same as previous cases. And in here, I just need to use W1 and H1. That's it, right? You don't have to use the numbers. It is very useful when we have a more complicated shape, and every time we can just change it in the parameter, and we don't have to change it in the geometry. Field selected, we have the geometry appeared, then we go to the form union and build on. So we are done with the geometry section, and we need to define the material. So the next step is to define the materials. But before we define the material, we should know that the solid mechanics define the linear elastic material model as a default option for our domain. But as you remember, we have a hyperelastic material, and we need to identify the properties as well. So let's right click on the solid mechanics and then go to the material models. And as you see, we have different material model options which you can use for your own problem in other cases. I'm going to click on the hyperelastic material, which is our case in here, and then select domain 1. And when I scroll down, I can see what material model is used in here, and we are not going to use this one. Our case is Muni-Rivlin 2 parameter, as I explained in my slides. If I click on that, I have the two material parameters that I need to identify, and they are selected from the material. Right? Now I have to go back to the material and define the properties. But before that, let me just change the out of plane thickness, or D1, right? So we are good for now. If we go to the material and then use blank material, we can define the properties over here. So you might be asking, why not we are using the material library? The reason is, this case we have a customized material, so it might not exist in the library, and we want to try defining it as a blank material, right? As we click on material 1, and then we have domain 1 assigned to it, we can define the model parameters, which is C10 and C01, and the density. We know them from our models. We can find them for a rubber. For this case, we have 0.37 megapascal for C10, and for C01 we have 0.11 megapascal, right? And for the density, it was this value, right? So everything is set for the material, and as you see, we have the parameters we need for a Muni-Rivlin 2 parameters case. Again, if I come back to the hyperelastic materials, we can see that this is the theory that is used for the model. You can find more information about it on internet, and these are the parameters that we need, which are selected from the material properties. Let's continue. Just change the bulk modulus, and the density is already taken from the material, right? So we are good with the material model, and we have to identify other boundary conditions from the physics of the problem. So again, if I right click on solid mechanics, we can identify a fixed constraint on this boundary, and if I get closer, I see that this one is selected. And then we need a roller or a hinged boundary condition on the other side, if you may remember from the model we had. So the hinged boundary condition is modeled as a roller. We can click on this one. So we have assigned a roller or a hinged boundary condition on this one, but we don't know which direction we have to restrict that. We want this to only move in the x direction, and there is no motion in the y direction. So we can simply go to the roller constraints, and on the normal orientation we use plane, and when we have plane we use y-axis. So now the roller is in such a way the boundary is only moves in the x direction rather than y direction. Okay, that's it for the two supports. And now finally we need to define the force. So let's right click and then go to the points and a point load, and then under point load I will select this point, and as you may remember I select this point because I want to make it to be not 100% at the center or symmetrical. Because we want to have a local buckling, we should do it in this way. The other option is we have an X force in this boundary and a tiny force in the Y direction. Again, you need to review your lectures on local buckling if you want to understand it much better. Okay, let's go back, and when we do so we have to define the amount of force. For here, for the X direction we can use minus F. As you remember, in the parameter section we define F as 0, so nothing will be applied for now, but in the future we will change this because we have defined it as a parameter. Okay, so we are all set with the physics. For the meshing, I'm gonna click on mesh 1, and then I'm gonna use finer, just select on build. That should be fine, it's small enough, right? Now the important and interesting part, which is the parameter sweep. If I go to study 1 under the stationary, we have to change the force from 0 to a specific amount. For now, if we select compute, it takes force as 0 and nothing will happen. But if we go to the study extension, then scroll down, we have the auxiliary sweep. We just select it. Now we can define the parameter that we want to change. If we use this add, we have different parameters, right? We can also change the width, the height, the outer plane thickness, but for now we just select force because this is the parameter that we want to sweep on, and as you see the unit is Newton. So to define it, I would define as a range from 0 to, we need a number to make sense. We can do some calculation based on the properties of your material and the dimensions. I know that for this case 0.0025 is a good number, and we have to define the steps. So I want to make a very small step. For example, I can use 0.0005, right? Or even smaller, let's use 0.001. I think that should be fine for the force range. Like I said, it's a very slender rubber-like material, which means that we need a tiny force to make the buckle. We can also find that based on the calculations, right? I think that's enough. So this is the part that I wanted to insist on, which is how we can properly sweep a parameter, which is very useful when we want to see the effect of changing that parameter on the simulation results. And we are all set with that. We can have other parameters. So imagine the case you want to see the effect of changing the width of your structure. We can have a range on it. Sometimes you may have multiple sweeps, but for now let's only focus on changing the force. Okay, so what the software does, for each number the software solves and then go to the other one. So basically, depending on the interval, the simulation may take shorter or longer. For now it should be fine. After we define that, we don't have to touch anything else, and then we click on compute and wait for the software to solve. You may know that this time we have a longer calculation time because for each interval the software should solve separately. So let's begin. Okay, the problem is solved and we have this nice picture. Let me zoom in. This is the final state, which means the final position of the structure at the final amount of force, which is 0.0025. As you see here, and this one is actually our stress results. For different forces, we can have different shapes. In fact, at the 0, there is no deformation or there is no stress, and then as we increase, more stress is generated in the system, and the more force, the more stress. In fact, we are sweeping on the force value, and this shows how the force values are changing. Let's see the actual deformation or the solid displacement. So if I right click on results, 2D plot, then I scroll down, I add a surface, and on the surface you see the solid displacement is already assigned in here. So then we click on plot, we have the displacement, the maximum for this point and the minimum at this point. We don't see it, right? So we click on deformation and then plot. So you might be asking why it looks like this, because we have a scale here which makes it smaller. If we want to see the actual deflection or displacement, we change the scale factor to 1 and then plot, and there you go. This is the shape that we are looking for. In fact, the x component is the displacement in x direction and the y component is the displacement at y direction, right? So if you want to see other points, let's just change the force, right? If we plot, say for example at 0.001 Newton, we have a smaller amount of deflection, and then at this amount we have more, and eventually we have this shape, which is the shape that we were expecting. It mimics the condition that we have a rubber holding with our two hands, and we try to approach the two ends to each other, and we get a huge deflection, right? It's very interesting. So now let's make a video out of it. If I go to the export and then under animation we click on player, and then we can see how to make it. So what we are going to show in the animation, this is our 2D plot group, which is our displacement. Same as the previous video, you can change the name so that you can find it in here accurately. The loop over, which means that what parameter we are going to consider as the parameter that is changing in the video, which is force, right? There is nothing else. But imagine the case that you have multiple sweeps, then you need to select it properly. If I scroll down, number of frames, we want to have all of them, which is 25, and in here it shows at different conditions, and if I move forward I get more and more. Let's go back to the original position where the force is 0. In the video we can adjust how long the video holds on each frame. So for now we have 0.1 second. Let's increase it a little bit to 0.3, and that's it. Let's say show frame, and if we click on play, we will see how it deforms as we increase the force. Very interesting, right? Let's also export it in a file for our report. So if we right click, go to animation and file, we select this file, we want to have an output movie, we can have different formats. I select this one. We can also browse and assign the folder, and I will do it on my computer. How many frames we have in each second? It's 10. I think that's quite a lot. Let's make it 3 to have a slower video, and the loop is over F. And these are actually the quality of the video. You can increase the quality if you want, but I think it should be fine. I think everything is good. Let's click on export and see the video. It may take a while to have the video exported, and now it's exported. I want to open it on my computer. There you go. This shows the deformation of the structure as we apply the force. Very interesting, right? Let's watch it one more time. And that's it. I think we have done what we wanted. and we got the result that we were looking for. Thank you and stay tuned for the next videos.